Welcome to the course on molecules in motion. We have covered till now we have covered at least 13 lectures, and we had majorly started off with motions of molecule in the gas phase. Now what we are looking into, we have started already as how the ions are transported in a medium which is not gas but a liquid. So, when we are looking into that, we are going to be focusing on various type of solutions or liquid phase, and majorly what we will look at is what we call as electrolytes. So, when we are talking about molecules in motion which is in a liquid phase, what we are trying to do is to get an insight into the nature of molecules they existing in the liquid phase and how they are moving in the medium, and that can be obtained in the previous classes. We had discussed about what are the experimental like measurement of viscosity. From there we had a crude understanding of the ions or molecules being moving in the solution. But when we are talking about a solution phase, essentially a liquid phase, then what we are studying is the motion of ions when we are talking about an electrolyte. Electrolytes are systems which when or substances which when dissolved in the medium or a solvent, they ionize to give the respective ions. So, the motion of the ions in this electrolyte solution is what we are going to focus on, and whatever important information we have, particularly of these ions. When we are talking about ions, they are going to move, and we are going to talk about the transport of various properties when through their movement, and when they are moving in solution, and if it's electrolyte, what we are essentially looking into, these species which are dissociated are charged species, and they will be dragged, the charged species means ions, they will be dragged through the solvent, whatever solvent medium we are using, on application of a potential difference across two electrode immersed in the sample which is containing the electrolyte. So, if you are looking into the picture like this, you are having, suppose you have an electrolyte. When electrolyte means if I have a salt which is like sodium chloride, which is going to ionize in water into Na plus and Cl minus. If we have that in solution, what we will look into, we have this are the sodium chloride crystals which we have added, and when we dissolve it, what happens? They become ions and they are dispersed in the solution medium. So, what is essentially the focus being the electrolyte substance, they form ions in solution, and these ions when across a potential gradient will conduct electric current. So, if you have electric current generated, that is a reflection of the ions moving in the solution medium. Whatever information we are going to have for the ions, we are going to essentially talk about ions for the first coming few lectures, and we will see the equations which we derive for these ions can be extended to a system for a neutral atom moving in solution. So, the empirical equations which we had talked about in previous classes in terms of the flux of matter being transferred when the particles are moving in various phases, that will be derived again, and for this whatever is derived for the ions will be extended or seen how there can be applied to a neutral molecule. So, when we are talking about the electrolyte, we are talking essentially, I am not going to talk about the type of electrolyte right now. I am going to give you a just overview, because we are going to look into the types of electrolyte in a later class. So, electrolyte is a substance which I have already discussed or talked about, which is going to yield ions when in solution. They are going to ionize and give rise to ions in the solution medium. And this is the evidence of the ions moving is from the electric current we obtained when a potential difference is applied across the solution through two electrode system. I don't know whether you have heard of another term which is known as polyelectrolyte. Polyelectrolyte means a substance which is going to yield ions in solution, right? So, what is a polyelectrolyte? Polyelectrolyte is a type of polymer actually. Like when you talk about big molecules, big structures, they may be having they may be also be ionized when in a particular solvent medium which we are taking. So, similarly, when we are talking about a polyelectrolyte, what we essentially mean is it's a polymeric or macromolecular system. Okay. So, these are molecules of huge size. So, these are going to be, when put in the solvent medium, they are going to ionize. The examples of such systems are if you have ionization of acidic groups in a DNA molecule, or ionization of the acidic or the basic group in a protein. Protein and DNA are structures which are huge, these are macromolecules. So, whatever the solution they generate when they are put in an appropriate solvent medium, so that they ionize. So, these acidic groups and basic group, when they ionize and the material is a polymeric material or a macromolecule, then the resultant solution which we get is known as a polyelectrolyte. So, polyelectrolyte is essentially an electrolyte system composed or comprising of a macromolecular system, starting from a macromolecular system. Okay. So, when we have an ionic crystal dissolved in a solvent, what happens? The ions are supposed to be, when in a crystal form, they have a definite lattice, they are sitting in a particular position and they are strongly bonded to each other, as we have seen in the previous slide when we are talking about the sodium chloride crystal. This is the lattice structure of sodium chloride. You see how compactly the crystals are sitting, atoms are sitting in the crystal. So, they are all bound together. So, what you are looking at is a crystal of sodium chloride with the lattice points being the being composed of the sodium and the chloride ions. Okay. So, when we are having a ionic crystal will definitely give rise to an electrolyte system. When they are dissolved in an appropriate solvent, what happens? The ions break from the crystal structure and give rise to a solution that contains the ions in the solvated form. What do we mean by this term solvated form? When you have a liquid, when you have a solvent medium and you have a particular crystal, ionic crystal, that means it is going to be comprised of a positive charge and a negative charge atom in the lattice structure. So, when the ions like sodium chloride is dissolved in water, what happens? The ions sodium chloride is dissociated in the form of Na plus and Cl minus. When in the solvent medium, they get solvated. What do we mean by solvated? We mean that the solvated molecules are surrounded by a sheath of few solvent molecules bound to the ions through electrostatic interaction. And when this travel through the solution, they travel on application of an electric field, they move as the solvated ion. Am I clear? What we are looking into, the solvated term solvated indicates that the ions in solutions are surrounded by a sheath or few layers of the solvent molecule that are bound to the ions by electrostatic forces and traveling through the solution in this form along with the ion. Okay. So, when we have a system which is a sodium chloride in water type of a system, where you have the ionic crystals dissociated, sodium plus and chloride minus, in a water medium, then the sheath which is forming around the cation or the anion, these are actually the water molecules. So, these are the water molecules which is surrounding the cations or the anions. So, these are actually solvated. When they are, the medium is water, then we call them as hydrated. So, hydration takes place, solvation is this type of solvation when the solvent molecule is essentially the water molecule, then we have the hydration. We can, this is a specific case when we call the solvation as hydration. Okay. So, whenever the ions are moving in this solution medium, we are essentially looking into the movement of ions, and we are going to now take up the basic concepts associated when ions are moving in against a potential difference. We are going to look into the basics just a while from now, but what we are trying to see is when the molecules are when a crystal is, when a substance which is supposed to be an ionic crystal is dissolved in water, they ionize, they break the crystal structure, the lattice bonds are broken, and what you have, they are in the form of ions in the solution, dispersed in solution, and each of the cation is surrounded by a sheath of the solvent molecules, and these solvated molecules move, these solvent molecules along with the cation and anion move in the medium when they are subject to a potential gradient. Okay. So, before we go into the concept of what we are going to deal with, I think we should brush up our initial knowledge of what we are going to be using, because each term which cannot be explained time and again. So, let us recapitulate what we already know and some things which you may or may not know. So, whatever we are talking about is now is electrical conductivity, which is eventually the conduction of electricity, a transport phenomena where electrical charge is carried by the ions in solution, electrons or ions, and when they are moving through the system. So, essentially we had talked about previously how we have transport of mass, how we have transport of momentum, how we have transport of thermal energy. What we are looking here is slightly different from what we have dealt with previously. It is similar when we look into the equation which we, phenomenological equation which we are going to derive. What we are seeing here is the movement of ions, and these are charged ions. So, these what we are looking into is a transport phenomena where electrical charge carried by the ions or electrons are moving through the system. So, there is a charge transfer associated when we have the transport. So, the ions are moving, and what are they transporting? They are transporting from one point to the other some amount of electric charge. Okay. So, when we are talking about the electric charge associated, what essentially we should be looking into first is the electric current, because that is what we measure, and to verify whether the transport of electrical charge is happening, because this is going to be caused by the movement of the ions in the solution or electrons in the solution. So, what is going to be reflection of the movement? The measurement of electrical current. And what is this how is the electrical current defined as? Electrical current is defined as the rate of flow of charge through a medium. We can call it a conducting medium. Here, so what is the expression which we have? It is the rate of flow of charge. That means, if dq is the charge that is passing through a cross section of a conductor in time dt, then we have the current associated equal to dq by dt. Now, we have talked about flux before. Here we can also have another term similar to a term like that. We call it as the electric current density J. Initially we had talked about flux in the previous classes, there also we represent the flux as J. Here also, since the concept is the same, the electrical current density is also nomenclated as J, and this is the electrical current which is passed per unit cross section area of the conductor or of the medium. Okay. So, if I have the current electric current which is generated is I, and this electric current is passed through a unit cross section area of A of the conductor, then the J, the electrical current density, is going to be nothing but J equal to I by A, right. So, we can easily see what will be the unit of the current and what will be the unit of the electrical current density. Current, as you know, is equal to 1 coulomb per second, that is equal to, that is defined as 1 ampere. 1 ampere is defined as one charge of 1 coulomb passing at time of 1 second. Okay. So, 1 ampere or ampere is the SI unit of current. So, knowing that, you can easily find out what is going to be the current unit of current density. So, coulomb is defined as the charge transported in 1 second by 1 gram ampere current. Okay. So, instead of usually we define the current, we should ideally be defining the current in terms of the coulomb. Coulomb is the charge, but instead of the charge, we always represent the electrical charge transport in terms of the current, and that is in amperes. So, if we want to define coulombs here, we define as the charge transported in 1 second by 1 ampere current. Okay. So, you understand, instead of using coulomb as the basis of definition of the henceforth, we are going to have the amperes, and to relate the ampere and coulomb, we know that 1 coulomb is equal to 1 ampere second. Okay. So, the ampere is defined as the current that flows through a long straight parallel wires exactly 1 meter apart, will produce a force per unit length between the wires of exactly 2 into 10 to the power minus 7 newtons per meter. So, how do you define the current of 1 ampere? So, the current of 1 ampere is how it is measured, is how you define it. 1 ampere is defined as if you have 2 long parallel wires, conductors, 2 long conducting wires, they are held parallel to each other. The ampere, 1 ampere is defined as the current that flows through these 2 parallel wires, which are separated exactly by 1 meter, and will produce a force per unit length between the wires of exactly the force which is going to be generated between the 2 wires placed at 1 meter apart should be exactly 2 to the power 2 into 10 to the power minus 7 Newton per meter. This is how the ampere is defined. One current produces a magnetic field that exerts a force on the moving charges in the other wire. This is the force we are talking about. What is the force which we are looking into? We are seeing defining amperes in terms of the exact force which is exerted between 2 long parallel wires separated by 1 meter distance, and we are measuring the force per unit length which is going to exist between the wires, and that should be exactly 2 to the power 2 into 10 to the power minus 7 newtons per meter. This current is produces the whatever you have produces a magnetic field that exerts a force. One of the the current produced in one wire produces a magnetic field that exerts a force on the moving charge in the other wire. So, this is the force we are talking about. The force between the two current carrying wires can be measured accurately using the current balance principle. We are going to do certain examples of current balance for measurement of conductance or conductivity in a next lecture, but let us go through what we are having here. A charge is flowing. Charge flows because it experiences an electrical force. So, there must be an electrical field associated whenever you have a current carrying conductor, right. So, we need to have a conductor, and that has to experience must have an electrical field associated with it to have the current flow or the charge flow. Conductivity of a substance is defined as this. So, how will we define the conductivity? We are coming to conductivity because we are going to be eventually dealing with solutions which is conducting, and conducting means they are transferring current or charge or whatever through the medium, and whenever they are doing so, we are looking into the movement of the ions in the solution medium. So, whenever there is a flow of charge, it experiences an electrical force, and this electrical force is the electrical field E in a current carrying conductor. So, the conductivity can be defined. Conductivity is also known as specific conductance, which we are going to look into further in next class, but the conductivity of a substance is defined as nothing but the current density divided by the electric field which is existing in the current carrying conductor. Okay. So, J is the current density per unit electric field. Okay. So, we can say the current density is nothing but the conductivity into the electric field associated with the current carrying conductor. So, the E, the magnitude of the electric field in this expression you can make out. If you have this E is the magnitude of the electric field, what you can see, the conductivity kappa, K is the kappa is the conductivity, which we have just now said. The conductivity of a substance is going to be defined by the ratio of current density to the electric field existing in the current carrying conductor. Okay. So, where E is the magnitude of the electric field associated. So, from this expression, this is the kappa. So, this is the conductivity. So, you can make out this is directly proportional to the current density and inversely proportional to the applied electric field. So, we have higher conductivity associated in a particular medium of charge or in this solution if you have a higher charge density that flows for a given electrical field. So, for a fixed electrical field, which is usually we fix it by putting a voltage or a potential of an exact value which can be measured, because we usually use a battery or sort of a system to generate the electric field. So, this electric field which we are looking into, if that is held constant, then the conductivity of a particular species will be directly proportional to the current density of the charge which we are looking into. So, higher the conductivity, higher will be the current density. That means, higher the charges are going to be flowing per unit area, per unit time. Okay. Now, the reciprocal of conductivity, if you remember, is known as the resistivity. Resistivity rho is 1 by R. Okay. Now, this R is actually the resistance. So, it is also 1 by kappa, 1 by R. Both the definitions can be taken into account. So, reciprocal of conductivity is resistivity rho. So, if I have say a conductor in an electric field, then what we have, let the x direction be the direction of the electric field in a conductor. Then what we can say? We can say the electric field is associated, can be defined as Ex into d psi by dx, where phi is the electric potential at a point in the conductor. So, we can rewrite this. You just have to look at the previous expressions, where what we had for the expressions for I by A can be equal to, we can rewrite that in terms of the kappa into the gradient in electrical potential. Okay. And what is I? I is nothing by Q by T. So, Q by T is by area. If you can rewrite this expression again, this is Q by T. So, I can write the Q by T is nothing but this into the area, okay, with a minus sign. Where did we get this expression from? You just have a look. The expressions we are getting is a phenomenological expression which we had, where you have the flow of charge, the rate of flow of charge being proportional to the gradient in electrical potential in the conductor. Okay. So, what we have defined? We have defined the electric field as nothing but the gradient in the electrical potential phi with distance in the electrical conductor. So, if you look at this more closely, you have this equation resembling the previous equation of previous phenomenological equation, where you have the flow rate of any particular property proportional to the gradient of another property. Okay, the first gradient of another property. So, the flow of current in a conductor when there is a gradient in electric field potential in the conductor. Such a gradient can be produced by attaching the ends of the conductor to a battery. Okay. Now, let us hurriedly go into the this part. Consider an electric current carrying conductor that has a homogeneous composition and a constant cross section area. We are looking into a conductor, electrical conductor, a current carrying conductor that has a homogeneous composition and has a uniform cross section of say A. Okay. So, the current density J can be will be a constant at every point of the conductor. Okay. And the current density is what? We have done this before. The current density is nothing but the conductivity into the electric field existing. And the electric field is given is equal to the gradient in potential, negative of the gradient in potential across the distance towards which the charges are flowing. So, this is the electric field strength which we have. This is minus d phi by dx. It is a constant for, this is also a constant for at every point in the conductor. If it is a constant, then we can integrate this to the difference in the psi in 2 points equal to the E of the electric field strength into the distance in the distance across which it is flowing. So, in other words, if we can write this expression in terms of the finite changes in the say phi value and finite with the distance finite movement in the distance dx. So, since we have this expression previously derived, kappa is being J by E and J being the current density equal to kappa into E. So, we can rewrite J in terms of the kappa and E. This kappa into E, and what is kappa? Kappa we have defined as 1 by A into, sorry, J is 1 by A I by A, and that is equal to kappa into the gradient in the potential across the length L. Okay. So, if the length being of the conductor being L, so we can replace the dl dx with the L, then the magnitude of the electrical potential difference between the ends of the conductor can be given as nothing but, we have to substitute here, we substitute here instead of the electrical gradient in dx, we have a finite change in the electric potential with a finite movement in the x direction. Okay. That is, so if we want to find out the magnitude of the electrical potential difference across the ends of the conductor, that will be nothing but, if you take it out and rearrange, I by A 1 by kappa into this dx will be replaced by L. So, you have, this is the expression you get for the magnitude of the electrical potential difference that is generated across the conductor. So, that is nothing but rho into L by A into I. The quantity phi, absolute quantity phi, is actually the voltage, and the R is the resistance of the conductor. Then what you have, R equal to the modulus of phi by I, or the phi equal to I into R. I think this is an equation which we are quite familiar with, V by R. So, instead of V, we are writing the absolute values of the electrical potential difference, which is across the ends of the conductor. So, comparing the two values of phi, this is one value of phi we have, and we have one value of phi here. So, if we can compare the two values, this one and this one, what we can write? This was one value, this is the another value. IR equal to, this is resistivity into L by A into I gets cancelled. So, what you have, R is nothing, the resistance is nothing but the rho resistivity into L by A. So, R is the resistance, and the units for R is volts per amperes, or you can say it is ohms, and 1 ohm is equal to 1 volt per ampere equal to 1 kg meter square per second inverse per coulomb square. So, this is how we define that. So, resistivity has a unit of ohms, and its length, it is resistivity is ohms times the length, and it is going to be ohm centimeter or ohm inverse. Conductivity is 1 by rho, and so hence it is going to be ohm inverse centimeter inverse. The unit, the rho inverse is also known as mho, or it is known as Siemens. So, some important points which I want to cover before we proceed to the next class is, since we have talked about the kappa, we have talked about the rho. The conductivity kappa and its reciprocal rho depends on the composition of the conductor, but not on the dimension of the conductor. But resistance, what we are looking into, depends on both the dimension as well as the composition of the conductor. And for a substance, for many substance, kappa is independent of the magnitude of the applied electric field, and hence independent of the magnitude of the current density. That is for certain type of substances. Such substances are said to obey the Ohm's law. Understood? What we are looking is, we are talking, we are defining Ohm's law in terms of what is correct definition. A substance has a K value, the conductivity. The conductivity is independent of the applied electric field E, and hence is independent of the current density. So, if you remember what is the unit for what we have taken the unit for kappa is nothing but the current density into divided by E. So, if we have a substance which is going to be independent of the magnitude of the applied electric field and hence independent of the magnitude of the current density, such substances are said to follow the Ohm's law. So, the definition of Ohm's law, what we are looking in is the statement that K remains constant with change in E. Okay. So, for substance that obey Ohm's law, if you have a plot of J versus E, should be a straight line, right. So, if you have a plot of J versus E, it should be a straight line, and that the slope of that straight line should be kappa. And what sort of materials follow Ohm's law? All metals follow Ohm's law. Solutions of electrolytes will follow Ohm's law, provided the applied field strength is extremely small or not very high, and they reach a steady state condition. Many books define Ohm's law as R equal to absolute values of the electric potential by R by I, that means V by I. This is not exactly correct. This is simply the definition of R, and this applies only for certain, it cannot be defined for all types of substances. Ohm's law statement states that R is independent of the absolute value of phi or of phi and does not apply to all substances. It's just another point. When we are talking about kappa and rho, we look into the table. We have 3 or 4 parameters. Look at the metal. Copper is a metal, and this is an electrolyte. This is a glass is an insulator. So, the values of conductivity and kappa kappa and the resistivity rho is given in for all. So, metals have very low value of rho, right. Metals have very low value of rho, 10 to the power minus 6 order, and very high value of the conductivity. Okay. Concentrated solution of electrolyte, you see concentrated solution of electrolyte, you have a strong electrolyte will have a low value of say rho and a moderate value of the specific conductance or conductivity. What happens to a semiconductor like copper oxide? Substance, the K value is intermediate for what you have for a metal or an insulator, and a semiconductor insulator generally do not follow the Ohm's law. The conductivity kappa increases with increase in applying the potential field or potential difference or field strength. Okay. So, this concludes what we are going to be talking about. Is the next class is how do we do the measurements for conductivity. Thank you so much.